Hello class. So this is video 2 on section 5.3. On the previous video, we defined the area function, which is basically a definite integral where we allow ourselves the ability to change the right endpoint of the interval. Right? So the variable becomes the right endpoint of the interval, which is the same as the upper bound of the integral. And I gave you a picture here of an example of that, and then we also worked an example. Or if, for example, we wanted to find a of 2 here, the thing that changes is the right endpoint of the interval or the upper bound of integration here. Right? So we'll be finding the net area bounded by f and the interval 0 to 2. If we want to find a of 5, the only thing that changes is the right endpoint of the interval, which is the same as the upper bound of the definite integral, and we're calculating the net area on the interval 0 to 5 of f bounded by f. Okay? So we went through all that in the previous video. Now here, I want to derive something. I want to remember the goal of this section, which I mentioned in the previous video, is finally find the shortcut to calculating definite area. And as I've been kind of teasing in the previous videos, it has to do with antiderivatives, right? Because the definite integral and the indefinite integral have the same notation. So it would make sense that they're related. So let me work through that. So here I drew a picture. Again, I drew a continuous function f, and then it's a function of t because remember, we want to reserve the variable x for the right endpoint of our interval. Okay, so I have a function f of t, and I drew a couple things. Right? So first of all, what I have is I have the area from a to x, the net area from a to x. Right? That's that part that's just in light blue. So that part in light blue here, this would be just a of x. Right? The net area bounded by f on the interval a to x. Now, and then I also have it underlined here below the t-axis. Now, I also have in orange here the net area, and let me just make it a little bit more pronounced, the net area bounded by the function on the interval a to x plus h. So that there would be a of x plus h. Remember, the input is the input of the area function is the right endpoint of the interval. Right? The interval always starts at a for us here. Right? So whatever the right endpoint is, that's the input of your area function. So now let me erase those things so it's a little bit more clear to see. Okay. Now I have one last thing here. So I have this thing here in red. So let's say I'm not interested in the area from a to x or the area from a to x plus h. I'm just interested in the net area bounded between x and x plus h. So just this part here. Well, how do I find that area, that net area, in terms of the area function? Well, I wrote it here. Let me write it again. Well, I know what the whole area is in this large interval. I know what the net area is in this smaller interval. Oops, I went a little bit too far. What I want is the area in this interval. So what do? I subtract the area in the interval in orange minus the area in the interval in blue. What's that going to leave me? The area in the interval in red. So that's why I drew the interval so you see how this works. Okay. So I want to subtract the area in the interval in orange. From that, I want to subtract the area in the interval in blue. And that should leave me the area in the interval in red. So calculating that, the area in the interval in orange, as we saw, is just a of x plus h. So the right endpoint is x plus h. We want to subtract from that the net area, which is area here because everything's positive, but the net area in the interval in blue, well, the right endpoint of that interval is x. So that's a of x. Okay. And that gives me the area precisely in the interval in red. So that gives me precisely this part here, this net area. Okay. And again, I drew the intervals below so you see what's going on with the intervals. Or you can just look at it as a picture and see, okay, I'm subtracting the net from the net area of the whole thing. I'm subtracting the net area of just the region in blue, and I get the net area of the region in red. Okay. Now, what am I going to do with this? Let's say I want to approximate that area with a rectangle. Okay, so the area in red. So I'm just going to use one rectangle, which of course is not a great approximation, but it's going to work for what we're going to be doing here. I'm going to use one rectangle in a left endpoint approximation, meaning that what I'm going to do is I'm going to have the length of the interval. So this length here, which as we saw is the same in red, is just h, right? How do I know that's h? Well, this input is x, this input is x plus h. You want to find how much is the length between those 2 points, just subtract them. Right? So that length is h. That's going to be the length of our rectangle. Now I want the height to be given by the left endpoint, so I'm going to go up here, and that's going to be my rectangle. So this is going to be an approximation for the area. Okay. So the exact area is a of x plus h minus a of x, right? We found that that's the exact area. And we're going to approximate it with this one rectangle, which is just one rectangle approximation using the left endpoint. So what's the area of this rectangle? The length is h, which is what we've seen. We just find the length of that particular interval, and the height is given by the function value evaluated at the left endpoint. The left endpoint of this interval is x, so evaluate the function there, and we get f of x. And so we can approximate the area in that region, the net area in that region, by h times f of x. Now, of course, I can rewrite this a little bit so it looks more similar to what I want. And so I'm going to divide both sides by h. Obviously, h is not equal to 0. I can make it more clear. H is not equal to 0. So I can divide by h on both sides. And what I get is that a of x plus h minus a of x, which again is the exact area in red, divided by h is approximately f of x. Right? By just rewriting this first not equation, let's say approximation. Now, right now, it's maybe not clear why I'm doing this, but let's go ahead and now go to a new slide. Right? So I was using this picture so you understand where all of these things come from. So hopefully you understand where a of x comes from, where a of x plus h comes from, and where a of x plus h minus a of x comes from. And finally, how this is an approximation by using one rectangle with the left endpoint as the height of the rectangle. So hopefully this picture makes all of that clear. So now let's go to another slide. Let me rewrite what we had. We had that the area in red here, the net area, and I'm gonna, well, it's approximated by h times f of x, where h was the length of the rectangle, and f of x was the height of the rectangle. We're using to approximate. Then from this, we divided by h on both sides because it's greater than 0, so we're not dividing by 0 here. So this is approximately f of x. Now, hopefully this looks familiar. Remember, a is a function, right? A is a function of x, where what's changing is the input, but it's a function of x. What does that look like? And if it's not clear yet, let me do something else. Let's say I take the limit as h approaches 0 of both sides. Okay. Now, hopefully, now this is exactly clear what's going on. What is this here? If you go back to when we first started talking about derivatives, this is precisely the definition of the derivative of a, right? Or of any function, in this case a. But what do? You take a function, you input x plus h, you subtract the function, you divide by h, and take the limit as h approaches 0. That is by definition the derivative of a. So assuming this exists, remember that sometimes the derivative doesn't exist, but assuming that exists, so let me write here, let me make a note. So here, assuming that this limit exists, what do we get? Well, the left-hand side, as we saw by definition, is the derivative of the area function. Again, no matter what the function is, that's the derivative, assuming that that limit exists. What do we get on the other side? Well, this limit is in terms of h. The function f doesn't have any variable h in it. So remember, whenever you have an expression, and you're taking the limit of that expression, and the variable that you're taking the limit of is not there, then basically you take that expression to be a constant. Right? So for the purposes of this limit, this f of x is a constant, right? Because there's no h's there. So what's the limit of a constant? It's the constant itself. So what do we get here? We get that a prime of x is approximately f of x. So what is this saying? We can that the area or let me say it like this: the derivative of the area function is approximated by the function f. Now, it'd be nice if this were an equality, right? Why? Because if this were an equality here, so let me make a note here. If we had an equality, what would that mean? Then the area function would be an antiderivative for f, right? Because remember, that's what an antiderivative is. An antiderivative of a function f is a function whose derivative equals f. Right? So if we had an equality instead of an approximation here, then a of x would be an antiderivative for f. Okay. What does the fundamental theorem of calculus say that we're going to see in the next slide? It says that, in fact, this is an equality. So it turns out that the area function is an antiderivative for the function f. And that's crazy. So we're going to see that in the next video, so I don't make this video too long. But remember what we were doing. We had this function f of t, just any continuous function. I wrote down two area functions, right? A of x and a of x plus h, right? So the net area bounded on the interval from a to x, and in orange here, and the net area bounded on the interval from a to x, that interval in blue. I wanted to find the area or approximate the area just on the interval x to x plus h. By looking at the picture, we saw that the exact area was given by this expression. Just take the area of the whole thing and subtract the area on the interval a to x. And then we saw that using one rectangle with the left endpoint approximation, we can approximate that area with this expression. Right? And then from all that, just going through, just rearranging and taking limits, we saw that our original function f is actually an approximation for a derivative of a. Right, so that's what we concluded. And we'll see in the next video that this is actually an actual equality, which is going to mean for us that the area function is an antiderivative for f.